Okay, I think we can continue. Nothing seems particularly off. So if we're going to continue, we should make sure that our function types are now compatible, right? So if we use alpha inside the post-compute data frame, inside that we still have pre-compute. Okay, so what can we do inside this? Post-compute. But remember that we have when we do the pre-computation, we have something like this over here. Instead of having it, the eligibles directly available inside the original data frame, we sort of had this. Yeah, so now we have arranged the eligibles inside this data frame. So let's try to do. I think we can do this again. So alphas go to that. Alphas append. And then we have alpha df equals to sub.df. Sorry, p.concat. Alphas x is equals to 1. Alpha df columns equals to instruments. And then this is the operation we want to do to update the eligibles df. So let's try something like let's take a look at how this looks like and how this looks like. So this is available to us inside the alpha1 class because we're doing this over here in post-compute, and we already did this operation here. So by the time we arrive inside post-compute, we can have access to this. So let's take a look at what this does. Right. Okay, this is inst is a single, is a string we want to pass in a list. So let's try that again. Okay, we wanted something along the lines of okay, so this is the alpha data frame, then we have this eligibility data frame. So I'm wondering if, but by the way, the reason why these are all zeros is because I'm loading the data frame from the disk, right? So when I started recording these lectures, it was the 2nd September. It was 2nd September, and now, so I haven't updated data, but today is 5th September, so we're not going to get any new data here, which is why we get 0 values. And that's okay, I mean, if I disable this, if I delete the cache, then we will get more updated data, and this you'll see what is over here. But we're just going to use the data on the disk. It's fine. Okay, so I think we're going to do something like input. I want to see how this looks like. So alpha df and see if that works. Right, so. So this is the alpha data frame, this is the eligibility data frame, and we get to do like an element-wise comparison. So in this case, even though these are the alpha data frame is available to us, the Boolean mask is set to 0. So here we will have false. So here is considered as unavailable for trading because we don't have market data. Like we said, right now we're using this disk dataset from our that is cached inside our own disk on our computer. So, but everything works as expected. So instead of having this, so now post compute, we want to do something like this. So we're going to do something like select originals here, equals to select here, and I think it will also be nice to have market here because it would be nice to instantiate. Because if we put this inside post compute, it means that we can access it inside any function. So later we can just access it inside of the compute signal distribution. So that means inside alpha scores, we can do alpha scores inside sub alpha df, the lock. We are basically just accessing the entire row, so I think we get something like this. So here. Okay, let's just maintain this now. Okay, so of course. So right now, until now we haven't done really anything interesting to get us to right now we haven't really used this eligibles array, right? We're just assuming that the entire GFC universe is eligible for trading, but that's not the case because inside the original code we had some filtering. So we will need to adjust to take only eligibles. So for example, here we take only eligibles. I think other than that, most of the logic remains the same. And inside here, you can also see we're just taking all the forecasts. So we would have to modify this function to return an array instead of a dictionary. So that's that. Okay. Okay, so let's continue. So we say that we want the forecast to be an array. So we want this to be an NumPy array, or at least a panda series, so that we can do this vector computations together. So we're using this alpha class. Okay, let me take a look. Right. Okay, so the reason this is a little bit challenging. Okay, let's see what we have here. So, for example, we could do alpha scores. Right. Let's try to run 3, find 8, find the I. See what we got here. Okay, so it's saying that here we'll do self-appropriate df. Then this will stop complaining, so we'll just create a pointer here to self.portfolio, so we don't have to keep repeating self dot. Right? Okay, so these are the alpha scores. Okay, so this is the first study, but so imagine if you get something like here, self.alpha df, you will see a data frame of the alpha scores. Okay, but the problem we have here is inside this alpha scores, I assume like this are already populated with values. We're only interested in the eligible part. So in order for us to do vector computation, then we're going to have to do something like alpha scores is equals to alpha scores. Right, this is because this is an array, so we're going to have to do something like dot index of. So we have index of self dot index of inst for inst and eligibles, and then this is going to give us the self inst inst dot index of inst. So this is the alpha score, but this is actually the thing that we're concerned about, because this alpha score will also contain the ineligible alpha scores. So this is a little bit problematic, because then we're going to do this for loop inside here, right? And then we're going to have to do something like so this is like there's an implicit for loop here, and then we're going to have to yet again get another array of forecasts. But because we're doing vectorization, we're computing the positions. This one has to be the same size as this and not this, which means we will have to compute this forecast for the eligible stocks, and then go back again and then do this. Go back again and then do this forecast computation, and build the array for the whole universe. So this is where it gets complicated, right? So let me just demonstrate what I'm talking about here. Because we are using a forecast array, and this forecast array is the size of the entire universe, right? So this has length of the universe. But then we are only interested in a subset of the forecast of which this has the length of the eligibles. So suppose we have some alpha scores, right? Suppose we have alpha scores of the same length. Then we're going to have to filter out the alpha scores to the eligible alpha scores. Then we have to compute the forecast, and then we have to build back this large array so that we can then return this forecast. So this is very cumbersome and also very computationally a wasteful resource. So in order to do that, that's where we're going to make use of this over here. Okay, so suppose we have this alpha data structure. We have an alpha data structure, of some dimension, and we have an eligible data structure of the same dimension. So we want to actually rank this alpha data structure, but remove those that are not eligible. So what we're going to do is we're going to take alpha divided by eligible. And what happens is, we'll get a data structure with the same dimensions, right? We get a data structure with the same dimensions. And then inside here, we'll have some infinity values, negative infinity values, then. And then we're going to say, okay, now convert all of this. So these are x real values, right? So convert all of this infinity and negative infinity to nan values, right? Because what happens if we sort this directly, the positive infinity ones will get the highest rank, and we don't want to regard them in the ranking at all, right? We want to just completely exclude them from the ranking. So we'll set them as NaN values, and then we will sort. We'll call sort in this, and then it will sort basically. It will just ignore this NaN values and do the sorting. Right. So it will basically just do this sort operation. So let's see how that works inside code. We're going to do this inside post compute, right? And instead of doing this in the compute signal distribution, remember I said we can literally do it anywhere, so we're just going to do it here. So we want to have something like self.forecastDF equals to forecastDF, right? And then we're going to make this forecastDF. We're going to see how we build up this data frame. But inside here, all we're going to do is have forecast equals to forecast self.forecastDF, and then we're going to go to the date, and that's about it, right? By the way, this value is just accesses the underlying numpy array, so then the computation is faster. And then here we're just going to take the absolute value, and we're going to take forecast. So that's good. This .lock allocation .lock operation is fine because, like we said, .lock is okay for a row access operation, even though it is not very fast. Ideally, we want it to be faster, but if you're accessing an entire row, it's okay to do that, to make that call. And the reason why we don't move this forecastDF into the data generator generator function is because this forecast data frame is specific to this post compute function inside the alpha1 class. So it is not a general data frame. Like in every single data frame, we would have, in every single backtest that implements this alpha class, we would need access to closing prices so that we can compute P&L and things like that. But in the general case, we might not need this data frame. So that is why we don't put this inside this zip data generator, and we would, in order to make it general enough, we would do the access here. So how do we build this up? So we can look at this input self.alpha data frame. So this is what we printed, right? So this is the alpha data frame that we printed. What we're going to do is we're going to take self mask data frame equals to self.alpha data frame divided by self.eligible data frame. Mask says that if you are not valid for trading, then you'll set it to 0. We'll show you later how it looks like. So mask data frame. So non-traded, non-eligibles equals to self.eligibles data frame dot sum. So sum across the columns, right? We take rank data frame. Goes to mask data frame dot rank. We'll rank across the rows. We'll do averaging algorithm, and then we would keep all the invalid numbers, and then we'll sort it in ascending order, and then we'll say we will short this amount. So rank TF dot apply. We'll apply this to the columns. We'll do it to the underlying numpy arrays. We'll put in a lambda function that compares the lambda function to the num-eligibles dot values over 4. So this is less than equals to, right? So this is basically implementing what is going on here. Lambda calls. Okay. Then we'll take long data frame equals to rank data frame to apply lambda. We'll again apply this to num eligibles divided by 4. Call security and np ceiling x is equal to 1 or equal to true. And then it's complaining because we don't have this here. So what does this do? So suppose we have 10 stocks, right? Then we'll take 10 divided by 4, which is 2.5. So we'll treat rank 1 and rank 2 as short. Now, if we have, on the other hand, if we have, assuming 10 stocks again, we'll take 10 divided by 4, so this is 2.5. 10 minus 2.5 is 7.5. We'll take the ceiling of that, which is 8, and we want it to be greater than that, so we'll treat 9 and 10, the 9 and 10th ranking stock. So this one, if you have 10 stock, we will short 1 and 2. This one will go long 9 and 10, so we'll take a long short portfolio basket. So it's the same as what we did for the previous sorting, basket sorting. Just a little bit more math, but not too difficult. And then the forecast DF will take short DF. We will treat this as a number, and then we'll treat the long data frame as type. We'll do the same thing. And then we will take the short will be a negative position, and then so let's take a look at what happens here. So let's take a look at what the algorithm does. We will generate a hold on. So what happens inside this algorithm? Okay, that's the big question. So this is the alpha data frame, okay, and then so this should be axis 0. Let's change all this input statement so we can walk through this slowly. Right. So 0 means apply to the column, and 1 means apply to the row. So that was a small mistake. So this is the alpha data frame over here. The mask data frame basically divides by 0. So if it takes a positive number and divides by 0, we will unfortunately get infinity and negative infinity. But inside the sorting, we want to just ignore it instead of having this infinity and negative infinity values. So, so what we'll do here is first we'll take df because to replace those infinity values and negative infinity values to nan. So let's try it again. Right. So once again, this is the alpha data frame. Then we will set all of these to nan, both positive infinity and negative infinity to nan, the number of eligible stocks for trading inside that universe. And then we will do the ranking while we ignore the not numbers. So we want to rank these. And then basically, we are not going to show this. You can print it. This is just, if it's lesser than equals to the first, if it belongs to the first quantile, then we will short it. Otherwise, if it belongs to the highest quantile, then we will go long. So that's how that works. Nothing too interesting. So let's try that again. So now we compute all of that, and let's see how our function goes. Right. Incompatible indexer. So what's happening here? So we actually haven't verified that this part of the code is correct. We're going to have to do some debugging. So what happens is here, we're trying to assign a non-scalar value. So we're saying that they're complaining that this is a series, right? Which means that here we screwed up. Actually, it's supposed to be numpy.sum. .numpy.apps. Actually, this is the same thing. This is just an L1 norm. So I think we do dot norm. We do positions as row, and we do order 1. So this is just the same as this function, right? So we're not going, so I mean, if you don't know what the L1 norm is, that's just a linear algebra term, so we're not going to talk too much about that. Let's see the rest of it. Positions equal to strategy scalar. Okay, so we just want to print positions here, so input positions. So let's see how the positions are. Oh, okay. Here actually we received the position to be 0, even though we are aiming for it to be an umpire array, which means the forecast chip was 0. So I guess on this date there was no eligible stock for trading, and the forecast chip was from 0. So here I think we can do np.zeros, right? And set their instruments. But actually we're going to just make it a little bit more general term. So for example, inside positions, this forecast that we just returned, inside this forecast could be things like, I don't know, np.n or -1, 1. So in our case, we have 1 and -1, but we could also have things like np.infinity, because very often we are dividing by the eligibility mask, right? So okay, imagine we have forecast and then we want to completely ignore those that involve non-eligible stocks. Right. So in this case, it's not a problem because we already set all of those to 0. But in the general case, suppose we have a forecast and we have an array of values, of which even those that are indexed as ineligible have values assigned to them. Then we can again use this to our advantage, right? So I think we're going to take something like positions. Okay, we're just going to set this to nothing, and then we see what happens to the positions, right? So if we get this positions, then you will see that on the days when the forecast chips are 0, then you're going to get very curious values, right? So you're going to divide it by 0, which means you're going to get all of these NaN values, which you don't want. So we're going to take things. What we're going to do is we're going to say positions equal to np.n.num, and then we do want to take positions. We want to do what we did over here. So copy and paste this line here, and we're going to do this to positions. So what other things are problematic? Anything with the division operator, right? So for example, nominal total, if the nominal value of the exposure is 0, then this is also going to be problematic. So we're going to say weights equals to this, positions, and then we're going to do the same adjustments to the weights. We say weight equals to this, and then we're going to append weights.